It is a pleasure for me to introduce the first speaker. It is Paolo Franchin, and he's from Sapienza University of Rome. And he will talk about the bridge classification and structural analysis. He was a member of project team 6 for Eurocode 8 part 3, and he was also leader of the project team of the Eurocode 8 part 2 bridges, which is the topic today. And he's currently also a really active member of the management group and the ad hoc group reliability basis of the Eurocodes. Furthermore, he's member of the editorial board of Earthquake Engineering and Structural Dynamics, and he's a well-known expert in all special topics related to seismic design. So now it's a pleasure for me to hand over to Paolo. So the floor is yours, Paolo.
Thank you, Christoph, for the introduction, and apologies everybody for arriving late. I have a flu, so I will not be very brilliant today. Let me start by sharing my screen. So I will be delivering the first and the last of these 5 webinars today. The first one, let me start with a comparison, say an introduction to this new second generation part 2. I would like to do that by comparing the table of contents of these 2 documents. And I'm assuming that those that are attending are familiar with the first generation Eurocode 8 part 2. The structure of the new document, second generation, is basically the same of the first one, but with some new entries, which are those that I have underlined here in yellow, which are new clauses that have been asked during the systematic review comments to the first generation Eurocodes, covering cable state and extra bridges. This is clause 9, and integral abutment bridges, plus something that was added on the way, which is an informative annex giving some additional information on timber bridges coming from the interaction with the timber committee, subcommittee 5. This notwithstanding, this increase of scope that was asked in the mandate for the revision of the Eurocodes, we managed to reduce the size of the document from 146 pages to 85 pages. So a relatively slim document. Most of these happened because there were, so it was not to our merit, is that there were a lot of replications in Eurocode 8 part 2 with respect to Eurocode 8 part 1, for instance. And so a lot of material has been removed or moved to part 1.1, like many of the things about modeling and nonlinear analysis, or by making reference, especially for anti-seismic devices, to the product standard EN 1529. Today, in this first webinar, I will talk about clauses 4 and 5, which are presented here. Basically the basis of design and modeling and structural analysis. I would say about all with the exception of these 2 clauses, with the exception of whatever concerns spatial variability of the seismic action and the methods of analysis accounting for this very important phenomenon for extended implant structures like bridges, because this will be the object. This is an area where major changes happened with respect to part 1.1 to part 2 first generation, and they will be the object of a specific webinar by Professor Sextos. So let's start with clause 4. Basic requirements. You may have already attended previous webinars on part 1.1. You know that importance classes that were used for reliability differentiation in the first generation Eurocode 8 are being replaced by consequence classes, which are those used in Eurocode 1990. So that there is an alignment with these 2 documents, and the definitions for the consequence classes is not given in part 2. So this has become, say, a smaller section. We just make reference to the definitions in EN 1990, which I have to underline. This is the table for from the Annex A2 on bridges from EN 1990 are an NDP. So each country may adapt these definitions to its own need. I would say that most bridges will fall within consequence class 2 or consequence class 3A. Consequence class 3A of let's say high consequence, the lower class of the high consequence class are all railway bridges on main railway lines, bridges over main railway lines, and bridges over and under major roads. I think this is very important. For instance, these what do we mean by major roads is not just, for instance, in terms of volume of traffic or velocity, like one thinks immediately to highway or freeway. It's also roads that have a major role, like, for instance, the only road that connects, I don't know, an industrial plant or a small town to the main road network. So this, say, includes issues of civil protection that were first presented here in the first generation. 3 slides on seismic action. The seismic action is defined in part 1.1, and design seismic action is given, the intensity is specified either in terms of, let me see if I can use, sorry, a pointer, laser pointer, yes, either in terms of return period or in terms of the performance factor. And the return period is a function of the limit state and the consequence class. The values that you find here are all national determined parameters. Both for TLSCC and gamma LSCC are the same that you find in part 1.2 for buildings. They are not different values. They all depend on target reliability indices that are now suggested in part 1.1, the target reliability for a structure with a given consequence class and the given for a given limit state. This is the relation for your information, and it's a relation that is similar to the relation between the return period and the probability of exceedance of the design seismic action. It's not the same because beta, the reliability for the bridge in this case, is a different probability. Is the probability of failure of the bridge, of exceedance of the limit state, not the seismic action. So just to tell you that this is consistent. And just to make a comparison with the previous generation, performance factors, formerly known as importance factors, are slightly changed. So, for instance, for the significant damage, for a less than normal important bridge, before this performance factor, the ratio of the seismic action was 0.85, now is 0.80, and for more important bridges, this was 1.30, now it's 1.1 or 1.25. These are all nationally determined parameters. So, an important aspect of seismic action for bridges that required a little bit of elaboration is how to deal with the topographic amplification, because these are not single point facilities, but extended structure. So guidance for the evaluation of the topographic amplification factor FT in bridges was given through this figure, through examples. And of course, what is important to note here is that since you have different points of contact of the structure at the supports with the ground, the surface, you will come up with a set of values, a vector of values that have T, and so you will have differential amplification in different points. What you do in the case where spatial variability is not considered for other sources, cases that will be explained in the next webinar, then you will have to average the topographic amplification factors and use an average value to amplify the uniform excitation applied to the bridge. Of course, this is all for the 99% of cases where you do, let's say, a regular fixed-based model or a simple model with SSI where you do not include the entire soil domain and topography, because in that case, soil structure interaction, topographic amplification are obviously not dealt with these factors, but part of the analysis itself. Now, last few words on seismic action, site considerations. So when you build the bridge, the site of the bridge may have some specific problems, like, for instance, the site is crossing, is in the close vicinity of an active or shallow fault. In this case, is the permanent displacement may arise, permanent ground displacement that are called co-seismic displacements. This is, let's say, one place where the code gives a recommendation, because this is, you see, a should. Okay, so ground permanent displacement arising from these causes should be evaluated, but it does not give indications, only few indications, because the problem is not yet amenable of simplified treatment, as I've written here. So you need to do specific studies in these cases. Everyone may recall the Paolo viaduct in Turkey, famous cases of problems on this type. The few indications that are given not in part 2, but they are relevant, are given in part 4, because and there are indications in an Annex E about these components of differential displacements. This is because, of course, pipelines are extended and planned like bridges, so they share this vulnerability to this problem. And then the other considerations regarding the site are the stability of slopes or liquefaction susceptibility. We're not dealing here, but there's not saying much about this, rather than mentioning it, because reference is made to part 5, and you can go and look at the webinars on part 5 for this issue. Now, some words on the characteristics of earthquake-resistant bridges, and in particular, the strategies that are recommended for satisfying the performance requirements, non-exceedance of limit states for the given seismic action. This can be achieved either by energy dissipation in members or in anti-seismic devices, or both. This is a common situation in bridges where you have a mixed strategy. And but note, please, you cannot, one should not intentionally use the foundations and the soil foundation system as a source of hysteretic energy dissipation. So this is the concept that has been advanced recent years, but mainly for reasons of access for repairs. This is not it is not recommended in Eurocode 8 Part 2. A further important issue is the torsional resistance around the vertical axis, global torsional resistance. The code, this was already in first generation, so nothing new. Should not rely on torsional rigidity of a single pier. So cases like this is okay, because of course you are fixed also at the abutments, but could not be, let's say, sliding at the abutments. And if you have a single span bridge, you have to consider this phenomenon and the associated extra actions for the dimensioning of bearings, of course. The distinction between primary and secondary members is a very important one. It's already in part 1.1, so it's something that you know from even from buildings and other structures. And supporting members resisting seismic forces in a given direction should be designated as primary. Now, this important sentence says that the number of primary members may be less than the total number of supporting members. This is better explained with an example. In the case of a bridge in Italy, for instance, over short piers or abutments, often you have sliding bearings, like shown in this, let's say, bearing arrangement here in this bearing plan, while maybe taller piers are, like in this case, connected to the deck, because the deck is used to restrain the top displacement of relatively slender piers. This was the design concept. And maybe you have the structure in, at least for moderate and high seismic action, connected to one abutment, so engaging with its vibration, the abutment through dampers or devices or a rigid connection. Well, A2, P3, and P2 will be considered in the longitudinal direction as primary seismic members, while secondary seismic members will be abutment 1 and pier 1. Of course, in the transverse direction, since these are unidirectional sliders, all members will be contributing to the seismic resistance and will be primary. The new, let's say, extra definition that is in this part 2 is that a sacrificial element, typically abutment back walls, that is in order to contain the size of deck joints, for instance, the cost, the maintenance can be designed to fail in the event of an impact with the deck, as long as they are easily repairable. So this is admitted by the code. For for sorry, I told you I'm not very well today. For the case where you exploit ductility, like in all elements where you exploit ductility in the members, like in enforced concrete piers, or as a mean to satisfy performance requirements, like the one that we were showing before, the structure should be assigned a ductility class, and this ductility class should be unique for the bridge. I want to underline here, before we talk about the Q factor, the structural, the behavior factor, that assigning a unique ductility class is not the same as saying that the Q factor should be unique. But the ductility class, which comes with the detailing, along with detailing, should be the same for all the primary structures. A second important thing that we should note about ductility class is that you cannot use any ductility class in any seismic action class. So, irrespective of the seismic intensity. The code says that for bridges in consequence class 2 or higher, this should be designed in DC class 3, in the ductility class 3. Once again, this means bridges that exploit ductility to satisfy the performance requirements. So there are other ways, as we said before, like seismic isolation to do to satisfy the performance requirements. But if you rely only on ductility for high for a consequence class 2, you should consider the ductility class 3 in the high seismic action class, and you should not use DC1 in moderate and high seismic action class. Of course, if you have a less than CC2 importance bridge, you can do it in DC2, even the high seismic action class. Finally, in the case where you have DC2 and DC3, meaning cases where you exploit ductility, because DC1, as we know, we only exploit overstrength. You cannot put plastic hinges, critical zones where potential plastic hinges can form wherever you want. Usually these are in the piers, and not necessarily in all piers. Coming back to the example that we have seen before, the deck in particular should remain within the elastic range. The only exception to this rule is when the deck is formed from, not the case that I've shown here on the left, but cases of bridges built through precast beams, simply supported, that are then made continuous to a continuity slab. These are usually allowed to form plastic hinges, but take care, these plastic hinges are not, they are allowed, but they cannot be relied upon for energy dissipation. They're not reliable form of energy dissipation, so they should not be considered in this respect. Finally, and very important, one of the few principles, you see, this is a principle, it's a shell. Unseating is a total no. We should avoid always unseating. And also, we should avoid pounding between adjacent parts that can oscillate and get in contact. It is very important. There is an exception, of course. We can have pounding and contact, for instance, when we have a sacrificial back wall, but this cannot be done in all cases because the deck must be tolerant also to this pounding and sensitive components such as pre-stressing anchorages. So if the deck is a pre-stressed concrete deck and you have anchorages at the beam head, well, in that case, you should take care not to avoid contact, and so that excludes the use of a sacrificial back wall. Of course, in order to size gaps, to avoid gaps and seating lengths, you need an evaluation of displacements. Displacements are given by this formula. It's the same as in part 2 from the first generation. And also, you need to account for second-order effects in structures that are sensitive to second-order effects. I'm not explaining this formula here because it's repeated later. So going to clause 5, modeling and structural analysis. In terms of modeling, the first issue for seismic analysis is model to perform seismic analysis is the masses. And of course, you have structural masses, but you have non-structural masses, and these are masses due to traffic or masses due to water for pier, and the mass of the entrained water for piers that are immersed. In terms of water, starting from the second thing, nothing has changed with respect to part 2 first generation, so I'm not commenting on it. It's one of the few, maybe the only annex that has been left to calculate the additional mass to add to the pier. And in terms of traffic, you have to add a proportion of the mass corresponding to traffic only on roads or railway bridges with severe traffic conditions. And these are the psi coefficients to account for these additional masses. Note that the load models for traffic are different, and it is specified which load models should be used, and in particular, only the uniform distributed portion of these load models should be considered for the evaluation of extra masses. In terms of stiffness, the other very important aspect, this is secant to the elastic limit for reinforced concrete members. In particular, for piers, is that are the places where we expect nonlinear actions if they are designed, if energy dissipation in members is considered as part of the seismic design strategy, then it will be, this effective stiffness will be the effective stiffness secant to yield, which is approximated as usual as 50% for the force-based approach, so regular, let's say, force-based design. For the deck, we should consider the gross stiffness. We consider that no inelastic action happens there, and we only consider a reduction to 25% for the continuity slab for the reason that we explained before. It is very important that this is the flexural stiffness. Torsional stiffness of the deck, as we know, when cracking occurs, decreases in a much more relevant manner. That is the reason why open sections or slabs are taken at 0%. So we basically neglect torsional stiffness of the deck, and we consider for box section a proportion equal to 50 or 30%, depending on whether they are pre-stressed or reinforced concrete. These are general prescriptions that need to take particular care when you are dealing with curved bridges, curved decks, because in that case, torsion contributes to the static equilibrium, so you need a more accurate calculation. This is a good point to define, to show the definition of skew and curved bridges in the code. So for Eurocode 8 part 2, a skew bridge is one where the skew angle is larger than 20 degrees. And the curved bridge is one where the angle between the tangent to the axis at one end of the deck with respect to the chord between the two ends of the deck is larger than 25 degrees. Of course, you can have both. You can have curved and skew bridges, like in this example. Skew is important, for instance, well, in many situations, but it's important for bridges that can in the seismic design situation, because this can usually leads to torsion around the vertical axis. This is because you have a resultant of the skew abutment that is, this is for the longitudinal direction, this is for the transverse direction. In all cases, you always have a resultant that has a lever arm with respect to center of mass, and this leads to a torsion around the vertical axis and an even impact. So it's mainly a dynamic phenomenon. The code simplifies the problem and allows, even in those cases where you use response spectrum analysis to evaluate the action effects under the seismic design situation, you can use an equivalent static moment, MT, torsional moment, to evaluate the effect of torsion. and I'm not entering into the detail of these lever arms that are a proportion of the size. This is true also for bridges that are not skew, but are relatively short, because they also tend to develop this type of torsional, this rotation around the vertical axis. This is important for modeling. When you have a large skew angle, like larger than 45, and your structure is supported on the abutments through bearings, so like a single span bridge, then you cannot use a single frame equivalent modeling. You need to model explicitly their position, the bearings, because you will have an uneven distribution of axial forces, and this may influence their stiffness, so also for the horizontal stiffness, and this is important for their torsional response. Finally, damping. Damping is this is not for the force-based approach. This is for response spectrum or response history analysis with the response spectrum with the elastic spectrum, just in case you use it, but mainly for response history analysis that you are given reference values of damping factors. These are basically the same that were in part 2 of the first generation with an added value for timber, in order to differentiate the damping value in response history analysis. Second order effects. The second order effects should be considered whenever the intermediate coefficients. This is the same as in part 1, so I'm going relatively fast. Second order moments over first order moments, and the P delta over V. When this exceeds 0.1, you need to consider second order effects. If this ratio is up to 0.2, you can simply amplify values from a linear analysis. Otherwise, you need to carry out a nonlinear analysis, and you have a limit for theta that cannot exceed 0.3. This is something that should have already been explained in the webinar on part 1. The way you compute the sensitivity factor depends on the method of analysis. So you take the values directly from analysis, values with components of Q to account for the fact that the analysis is done and that displacement, analysis displacement increases also due to ductility. Finally, a few slides on analysis. The vertical component of the seismic action can be omitted in low and moderate seismic action classes, and should be considered instead when you are verifying structural members of pre-stressed concrete decks, because of course pre-stressed members are sensitive to vertical loads, and or you have structural members in cable stayed bridges where you have the inclined stays and important axial forces in the pylon, or when you have anti-seismic devices that, as we will see in the webinar 2-4, may be very sensitive to axial force, or like in the case of inclined piers, like in this example shown here, where of course both components lead to important axial force variations in the members. The values of the behavior factors have basically not changed with respect to the behavior factors that were in part 2 first generation. They have been, however, split, so their contribution now are clearly separated into contribution of overstrength, which is 1.5, and in contribution coming from redundancy and ductility. But the end product in the end are the same. So I'm not spending words here on this. Something that has changed instead is the way you reduce, only slightly changed, the way you reduce the behavior factor to account for what? To account basically, I'm sorry, to account for the foundation flexibility. This was not present in part 2 first generation. The reference is to part 1.1, where you have when you consider soil structure interaction in your model, you you should reduce the ductility related portion, because the deformation absorbed by the soil foundation systems reduces the ductility that can be used within the structure. So you cannot rely on it. You will have a reduction for foundation flexibility, and then the usual reduction for high axial force or for non-accessibility of critical zones. If something cannot be easily repaired, you should not let it go into the inelastic range. And then for irregular inelastic demand. These are all things that were considered already in part 1.1. In yellow here, only in the case of bridges that are neither curved nor skew, you can actually use, even if the ductility class is unique, two different behavior factors in two directions. This is the typical case of a straight bridge, non-skew bridge with, for instance, wall piers, where you have available ductility that are very different in the longitudinal and transverse direction. You can use different values of Q. Finally, almost done, the nonlinear static analysis and nonlinear response history analysis, which are the analysis methods used to implement the displacement-based approach, meaning design with verifications in terms of displacement for ductile mechanism and forces for brittle mechanism. This is the usual, let's say, well-known single-mode invariant N2 pushover method. It can only be applied to straight bridges, so it means not curved more than 25 degrees, so small curvatures are okay, and with model mass larger than 60% in the two-plane direction. We don't need to explain this method. There is a permission, this is important, to use alternative methods and model pushover methods that are well known to people dealing with bridges and nonlinear static analysis, are mentioned in a note, but they are not explained. But let's say opening to the use of these methods is through this clause. But they are not like fully endorsed, and it is reminded that they have limitations and are not of general applicability. This is important. This means that basically when you cannot do regular N2, yes, you can embark in using a model pushover. There is a permission, but let's say the main way to go would be a nonlinear response history analysis. One important thing, when you can do N2, you can do independent analysis in the longitudinal and transverse direction, and also independent verifications. This is in the spirit of the simplified method. So I am done, and I'm here to answer questions. I think I used 4 of the 5 minutes for the questions. I'm sorry. I can't see anyone.
Thank you for the presentation. I can't see any further questions. So considering the progressing time, I would like to thank you again and lead over to Dietlinde to introduce the next speaker.
Thank you.